Okay. Welcome to Fluid Mechanics. So with this video, we're going to do just an overview of what this class is about, the structure of the class, and just some things to prepare you for the whole semester. So first, let's talk about the syllabus and class structure. Most of the content will be delivered through, let me get to this, there we go. Most of this content will be delivered through online recorded lectures, just like the one you're watching right now. It's me talking at you and you filling out scaffolded notes, right? Scaffolded notes. And scaffolded notes are really, really important. And we'll talk about this as the semester goes on, but one thing I want us to think about always while we're in the classroom is what I call active learning, right? Which means you're actively engaged in the material and attempting to do something to it besides just memorize it, right? Okay, great. So we'll also have synchronous lectures. This is the normal class time, and this will be a lot like office hours. So there will be, well, we'll see how this goes with the pandemic and everything, but we might have some group work. I will do quick summaries of the material for each day, but it won't be anything like the online recorded notes. Quick summaries, and we'll also do some example problems. Oops. Cool. Because of the uncertainty with the semester and, for being honest with each other, the likelihood that we'll have to possibly go remote again, we're not going to have in-person recitations. We're going to convert that, likely going to convert that into, we're likely going to convert that into office hours. So for the TAs. Our exams are going to be held in the evenings. There'll be 2 hours. We are attempting to schedule the time and location of those, but I'll let you know those on Blackboard for sure, and in lecture once we find them out in class. And we'll have a final exam, which is 3 hours of cumulative. Cumulative exam. We, as for homework, we are still working out the details on this, but we're going to do an online homework system. We're going to say online homework delivery but you will turn in written homework weekly, pretty much, with a written prompt. So the online homework delivery, we're kind of pilot testing an online homework system. The thing we don't like about online homework, and I'm sure the thing that you don't like either, is that we don't get to see your work, right? We don't get to grade your work. Nobody does. So for this time, what we're going to do is we're going to try the online homework system. You'll be able to test your answer in the online homework system and see whether or not the answer is right. But what you're going to turn in is your written work to get that answer, and we will grade the written work, not the answer, if that makes sense. So We will literally grade everything up to, but not including the answer in your written work. So all the algebraic work and things like that. The assumptions you make, the diagrams you draw, stuff like that is what we will grade. And there will be a writing prompt that's included in each homework. And that writing prompt is a short paragraph where you talk about two things. So in your written work, you're going to circle parts of your homework where you are stuck, where you experienced frustration and stuck places is what I call them. And then you'll also circle places where you had successes, right? Things that you were like, wow, I get this now, right? And then you'll write a short paragraph where you'll describe where and what you got stuck on and why you feel like you got stuck on it, right? And that's the hard part. Describing why you feel like you got stuck somewhere really engages the active learning. So let's take a moment now and talk about active learning. Active learning here. When I was an undergrad, and this has always stuck with me, I took a class on cognitive neuroscience because I don't know why, I was stupid. But it was a fascinating class. At the very beginning of the class, the professor said to everyone in the class, I'm providing you with all of my PowerPoints. Do not print them out and do not use them as notes. They're there just as a reference. If you take notes and you translate what I'm saying into words that make more sense to you, right? If you rework the concepts and don't just copy down what I say word for word, you will retain 60% more material in class, right? Which is an incredible amount. Think about that for a second. You're in class at least 3 hours a week, right? So 60% retaining 60% more material is like an extra 2 hours of studying a week that you don't have to do, right? And if you take that for every class you're taking, which could be what, 3 to 5, we're talking 6 to 10. Is that right? Am I doing the math right? Yeah, 6 to 10 hours a week of extra studying you don't have to do, right? And this kind of active learning where you're not just trying to memorize things, you're trying to understand the concepts and restate them in your notes, right? Is tremendously powerful. When I was in undergrad, I studied, well, I didn't have the greatest grades. But my grades became a lot better when I discovered a pretty unique tool. What I would do is I would outline every class before an exam. So what I would do is I take all the concepts and try to fit them into a structure, right? And the structure is the important part. I wasn't just writing down words that were related to the topics we were doing. And you could do that if you just do the syllabus and write them down, right? When you put them into an outline, you have to give the ideas a hierarchy, right? There's the first one, which is like 1, 2, 3, 4, and then you do A, B, C, and then you do lowercase a, B, C, and then you do I's or whatever, Roman numerals, whatever. So the whole point is, though, this hierarchy forces you to take the ideas and resynthesize them, right? And there are lots of ways of doing that. An outline is not the only way. Eventually, I became very good at, in class, writing down notes that were not what the professor was saying, not what the professor was saying, but what he was trying to say, right? But the point is the same. You're taking in material and reshaping it and outputting it in a different way. And that reshaping is where learning really happens, right? And so we're going to try to give you different ways of doing that. In this class, the scaffolded notes are one way in which we try to give you to do that. So with the scaffolded notes, I give you notes where the figures are already drawn. A lot of the structure of the lecture is already drawn, or is there, the words. But the important parts I have erased, right? And I'm going to fill them in my lectures. And then you're also going to fill them in when you're watching the lectures, but you're going to do it in your own way, right? So if I say something like scaffolded notes, right? you might call it something else, or you might put a little note here and describe it as notes without important stuff. Just something like that, where you restate it as notes without the important stuff, will make that stick much more in your head than if you just wrote down scaffolded notes like I did, right? In fact, we know it. It's on average, it's 60% more. Then I think actually, if you sincerely dedicate yourself to it, it's more than 60%. So we're going to do scaffolded notes. Before each exam, I'll help you run through an outline. And like I said, this is something that was very useful for me. So I'm going to do it with you, but I hope you find your own active learning tools that will help you really save your time, right? We're saving your time. Then there's also this written prompt, right? So I mentioned this written prompt here for the written homework. And this written prompt is kind of important. It's going to make you go back and look at your work, and again, think about your work in a different way. And when you try to think about why you were stuck in a particular place, not just that you were stuck, that's obvious. A lot of times you'll get to a spot and just stop, or your work will become, after you've graded a lot of years, you can just tell, right? Work becomes much more disorganized. The thread is lost, things like that. It's easy to tell where somebody got stuck. The important part is to go back and drill down and figure out what was the concept that was missing, or what concept do you feel like you would have needed in order to finish the assignment correctly, right? Now you'll notice that if you don't know that to finish the assignment, then it's really hard to pick that out, right? To figure out what you're missing if you don't have it. I totally understand that. And it's that work to figure out what you didn't know to finish that assignment, even if you don't actually finish the assignment, that cements the learning that you did and extends it, right? So with written prompts. Written prompts. In the past, I would do a lot of group work in class. It turns out that, people say you don't really learn something until you teach it. And the reason is because when you teach something, again, you're resynthesizing it. You're changing it from the way you were taught to the way you're giving it to other people. Because let me tell you, if you don't feel like you understand something, trying to go in front of a room of people, and even if you're just parroting back what you were taught, it feels false, it feels hollow, and you just terrified someone's going to ask you a question that you don't know the answer to, right? And group work kind of does the same thing, where it forces you to answer questions and answer prompts and rephrase things that you didn't think you were going to have to rephrase or answer, right? So group work in class is great. I try to do it a lot. This year, I don't know how that's going to work with social distancing. Last year in Zoom meetings, I tried to do it in breakout groups. I was partially successful. So we'll see how it goes, but that's another thing I do, is group work in class. And then we do something called quiz, not quizzes. So a quiz, not quiz is a response to something I discovered, was that when I held in-class quizzes, people actually learned a lot on the quiz, because the amount that their grade depended upon the quiz focused them in a really concrete way, right? And so what I've done is I've basically taken very particular example problems, ones that to me highlight concepts in the class very well, and we're going to treat them like a quiz, right? You're gonna do them in class, and you will spend all of your mental energy on that quiz. You're not going to be thinking about other stuff like you normally would be in class. You're not going to be messing around on your phone or anything like that. You're going to pretend as if your grade depends upon it, right? They're usually pretty fun problems too. But But the idea is to teach you to fully engage in the work in the moment, right? And to, again, use your time as effectively as possible. Cool. So that's active learning. Those are all the steps I'm taking. If you have any ideas about how to improve any of these things or add things to this list, I'm very happy to learn about them. Cool. So let's talk a little bit about why we are studying this material. Unfortunately, most of the classes you've taken follow a very, very well-worn structure. We give you a well-defined problem, right? I usually am the one who does this. So the professor / teacher is the one who does this is how it's been since kindergarten for you guys and me, I assume. I don't think education's changed that much in the last 20 years. And then you are supposed to determine a solution, right? And in the process, you're supposed to use the model to do it. Use a model / whatever the tools are of the class, right? Sometimes with math classes, you don't really have models. What you have is just math. But in the engineering classes, we've given you models, and you're supposed to use those models to come up with a solution, right? But this isn't how the world works in any way. So there is no such thing as a well-defined problem. You start with a need, and sometimes that's what you're supposed to determine, right? You're supposed to determine the need. And that leads to a poorly defined problem, right? And sometimes your job description, and I know people who do this for a living, is to take a poorly defined problem and turn it into a well-defined problem. And they make a lot of money doing this because large corporations will sometimes meet and be like, Corporation 1 tells Corporation 2, I need you to do this. Corporation 2 is like, that's great, but you're a little ambiguous. Let's hire somebody to make a well-defined problem that we can both agree that Corporation 2 is going to solve. And so Corporation 3 comes in, does that, and everybody's happy, right? It's surprising how often not having well-defined problems screws up contracted work. So anyway, that might be your job. Or maybe when you're just starting off and your job is to run some models. I had a job briefly. I didn't actually even show up to work once because I ended up going to graduate school before work started. But what they told me I was going to be doing is going to be literally running heat transfer code, so computational fluid dynamics packages on turbine blades. And I was going to be stuck right in here, in between conceptual solution and detailed solution, trying different things for other people, right? And that's because with aircraft engines, the stakes are so high. They're not going to have new people start anywhere else, but in the area where I could do the least amount of damage, right? So the idea, though, is that right, your job might encompass all kinds of different parts of this. And my goal, right, is to give you the tools that allow you to understand at the minimum how to use fluid mechanics models to help you do all of these things, right? To help you do all these things in your job. And that means we're not going to be sticking with well-defined problems as much as you might like, right? We are going to use some poorly defined problems. We're gonna find out actually about how the models we learn in class are flawed, deeply flawed in some cases, right? And so to do that, like I said, there's going to be some ambiguity, and that's what I wanted to tell you about. The important part, though, that I want you to know right now is that what we are going to be teaching you is models for how the world behaves, right? As engineers, what we do is we use models to predict how systems will behave, right? Now, here is an excellent case for active learning, right? I say we use models to predict how systems will behave. you should take that and rephrase it in some way that all still makes sense to you and captures the meaning of that phrase, right? You could say anticipate the future outcome of systems, or to calculate the outcome of physical systems. You know, there's all kinds of things you could do, right? Now, fluid mechanics, the class we are taking, is hard because in a lot of ways, the models that we will learn are disconnected from each other. Disconnected from each other. What does that mean? Well, when you take a class like solid mechanics, and it's not exactly true that all the models are connected, but a lot of the times what you learn in one section is built upon in another section, right? You first learn about moments, and you learn about vectors, and then you learn about how to calculate moments in a beam, and then you learn about how to calculate area moments of inertia, but you still need the moments of the beam to calculate that. And then you calculate twisting, and obviously I've never taught solid mechanics. I haven't taken it in 25 years now, so I'm not doing a great job of this. But the point is that everything that you learn kind of builds upon itself towards the end. Now, fluids is not that way, right? When we learn each section, they don't really build upon each other, right? So in theory, you could not show up for one whole section of the course and be completely fine for the end. Now, obviously that's not true, because oftentimes to solve a problem, we need multiple models, right? So we're going to need to draw upon stuff we did early in the semester and later in the semester to solve a problem. But those models themselves are not really connected, if that makes sense. The other reason fluids is hard is that fluids is subtle. And what I mean by that is the behavior is complex and varied and depends strongly on the context, right? And we're not talking about context that is easy to recognize, like the type of support that a beam has. I'm going to go back on solid mechanics here. Sorry, guys. Like, you could tell it's a beam simply supported. Is it, you have the different kinds of supports where one's a roller support, one is you can rotate about it, but it's stuck in place in X, Y, and Z, and one is it's stuck. You can't rotate and it's stuck. Those things are really well defined, right? And they're easy to see. Fluids is not that way. The assumptions we make are a lot harder to visualize, they're harder to recognize, and their outcome on the models that we use is great. We have these generalized equations, and after you turn the crank with the assumptions, they come out looking completely different, right? So understand so you cannot just memorize a few equations and use them on an exam, because those equations that you can memorize are never the ones you're actually using. You take the equations and you alter them based on the assumptions you're using, and the number of combinations of assumptions we have is so great that it's not impossible, but it's very difficult to memorize all of them. So you need to use the active learning techniques we're talking about in this class to actually understand what's going on, right? 3, the math is not trivial. It's not nearly as hard as it could be. Fluids is notorious for having difficult math, right? But that being said, we will be manipulating integrals and differential equations, right? Partial differential equations and triple integrals and double integrals, all these things we're going to have to be using. And you have to understand, even though we're not going to be doing difficult math problems, you have to understand the math in order to simplify the equations to get where we want to go, right? Since models are disconnected, knowing which model to use is hard, right? And since we often combine which models we use on a problem, it's not like you can just rely on using the thing we learned this week to solve this problem. Oftentimes you'll have to go back a couple weeks and decide, is that model appropriate for this problem or not? Can I use it to remove a variable and things like that? So one thing I've done, and I will see if it's useful for you guys, is I've created a semester-long design problem as a way of kind of showing how when we add these models into our toolkit, we can use it to refine a design in different ways, right? So we have what is our space tower? Right? Obviously you can read, right? What is our space tower? So if we draw this, we're gonna draw this. Here's Lake Erie. I like to imagine this rising out of Lake Erie. And then what we're gonna have is we're gonna have a tower coming out of Lake Erie with jets on it. Shooting water down, shooting water down in order to hold some kind of payload up higher into space. The idea is people are spending a tremendous amount of money right now figuring out how to get airplanes to raise rockets up to a couple miles higher so that they can get out of the dense atmosphere and be closer to space and save money on rocket fuel, I assume, and save money on launches. Why don't we just raise them up with a water tower? We could use electricity to run the pumps. Water is an endless resource. We shoot it out of our nozzles and it raises the tower up, and it's completely innocuous, right? Except for this thing's gonna possibly could be several miles tall and just like thundering supersonic jets. It's gonna be pretty epic to look at. But the point is that you're hopefully sitting up here in the stars. And here's the moon. Yeah. So what do we need? What do we need this space tower to do? Remember, we talked about the different design steps. What do we need this space tower to do? Well, one, it needs to support the weight of one person. Two, it needs to withstand the wind. Three, can't consume too much power. Four, it must be buildable. And five, must get as high as possible. And what's fun is that we will cover models in this class that help us predict these things, right? We will be able to calculate how much thrust a nozzle can produce. We can calculate how thick our pipe needs to be. We can calculate how much power this requires. And we can calculate what the drag is, what the drag force on this tower is from a given wind, right? This right here is the essence of engineering, okay? People come to you with problems. They say, listen, I want this thing to be able to withstand the wind. And you go, well, let me predict what the forces are on it. And then we can determine if we need to install additional jets that can counteract the forces due to wind, right? So you're calculating drag forces, you're calculating the thrust from each nozzle, you're calculating the amount of water consumed in order to do this, and whether or not your pipe is big enough to suck all that water up and supply the nozzles in it, right? You as engineers, what you do is you answer physical problems like this using numbers, right? Great. Like I said, we will learn models to answer all of these questions. Cool. So I'm going to stop here. The next section we're going to talk about is dimensions and shear stress, and we're going to do a new video.